anything surprise you about the algal discussions that we had? They're really complicated biological processes. Nitrogen assimilation is not a single step. It's actually very regulated in the environment. Nitrate uptake doesn't even happen if there's sufficient ammonium in the background in the water column. Plants won't use it because these nitrate reductase, that enzyme system is inducible. So it costs the plants actually more metabolic energy to acquire nitrate than it does ammonium. And so all of these we kind of gloss over when we start looking at submarine groundwater discharge with nitrate as the principal species of nitrogen that's present in them. There are biological costs associated with it, and I think when we start gaining more information that compares one species to another, we're going to start to see that species differ in their capacities. They certainly differ in their rates of these processes, and so this is where I firmly have come to the point in stating that species matter. The functional form is handy because it simplifies the diversity that we have, but in the end it sells us short of what the true complexity of the ecosystem has. And as a biologist, complexity for me is job security. Right?
Yeah.
You understand?
Yeah.
So can I ask a question then that in a reef that's heavily grazed, is there more ammonium available naturally because of the detritus of the grazers?
It could be. And yet it's probably taken up by the plant so quickly that it could be reflected not in standing water quality or water concentration values, but in more rapid assimilation by the plants and growth. Right? And so this is where I've moved away personally from endorsing water chemistry work because it's only a single snapshot, and the actual acquisition by the plants of the predominant nutrient that's available becomes really a good insight in integrating over a longer period. Does that make sense? So if the plants have been stripped of all their available nitrogen pools within that, say that's 75% of nitrogen tied up with photosynthesis, you've forced them by growing them under lights and not giving them anything but background nitrogen, you put them out in the light, they have to photosynthesize, they have to consume those pools. That's what we do when we strip our plants down to background levels. We almost kill them. 5 days, 7 days under those kind of conditions draws those nutrients down. Then when we put them out in the environment, they acquire everything as quickly as they can to resupply those pools and resupply the materials that are where all that 75% of the nitrogen and the other 25% go within a plant cell. So that's the basis for a lot of the work that we've done on Maui and subsequent studies by Dan Amato that I'm not going to actually talk much about today. So I think the water chemistry gives us a snapshot, valuable, but it's not as informative in the long run as what's tied up in the plants by their physiology.
Yeah, you just kind of mentioned, I don't know if they've all got that about it, you still working on it. So you actually take plants and put them in, you treat them first before you put them in the field to do things.
We started off not doing that, just collecting the plants and analyzing them, and that works out fine. And that if there's a strong, persistent signal, for say, of a wastewater source in the environment, we will see it because of the long length of time for that signal. But if you take a plant from the field where there's been a lot of nitrogen loaded into that environment, and then you take it in and put it in an experimental setting, the plant will not respond to nitrogen. It's already sufficient in its supplies. It won't acquire or grow faster. It's already growing at capacity. Something else is limiting it. We learned that the hard way when for about 2 years of work with Meg Daler and Mark Vermey, we were doing a number of different things, and the plants, we'd bring them in and we'd think, oh, this is great, and then they would do nothing. Right? And after a while you realize that maybe it's because their level of storage is already so high within the tissue that, especially for some of the sites in Maui where the ag sites or the wastewater sites have substantial loading into the environment, the plants are already sufficient. They're limited by something else. We saw that for the Cladophora work as well from samples on Maui. So by forcing them to draw down that nutrient supply, and then putting them out in the reef in a cage that allows them to not be grazed, they are then able to acquire all of that nutrient that's in the water at that time. And I think that gives us the advantage of actually having only a very limited amount of differential uptake of one isotope versus another, so that we are not seeing a lot of discrimination, because the plants are so starved they're taking everything. Discrimination at a isotopic level usually happens when an enzyme has a choice of substrate, like a carbon-13 versus a carbon-14. But if the plant its nutrient base is so deficient, they apparently don't prefer one over the other. They take whatever they can get. And so in that way, we've found with these experimental approaches a very consistent kind of response through the manipulation of the plants before we put them in the field, and then taking them out after about a week each patient. Does that make sense? Okay. So here are our invasive macroalgae, the ones that have taken off for one reason or another. These are all in that frondose category. They are all isomorphic in their alternation of generations for these top four. This one's life history is not even understood. We know so little about this alga that we don't even know what its gametes look like, what its reproductive structures look like. And yet, ironically, this is the thing that's probably changing reefs most dramatically. This is the leather mudweed from Mauna Loa Bay that's marched down around Diamond Head and is in Waikiki now. It will persist as everything else dies. This is a very tough, resistant plant. And yet, so this is a gap in knowledge. We need to know a lot more about this alga in order to better understand it and manage it. The one on the top is the Acanthophora. This species is one of the ones that we could commonly use for our Delta 15N work on Oahu and on Maui and Meigs island-wide sampling. This is the plant that actually was the most preferred alga in the feeding trials that were done in that early slide that I showed you that had the scarids and the acanthurids. This alga is eaten more readily than any other that we have. So it's not true that all invasives are unpalatable. They're actually invasive species, non-natives, that are preferred. So when you go to Waikiki and you see that alga this tall, what's that tell you? It's not enough grazing, right? Right? And so you can use some of this information as a kind of metric for getting a quick sense to the health of that reef. Hippium muciformis is the persistent bloom species on Maui. This had at least 3 different sites where it grew for years at a time. Gracilaria salicornia was restricted to Oahu. It was transplanted to Molokai in about 1990. It's now a mess all over the South Shore Reef on that island. This is Eucuma denticulatum, species closely related to Capophycus alvarezii. These are 2 taxa that are restricted pretty much to the windward side, mostly in Kaneohe Bay. So these plants, because of their weedy, invasive characteristic, I imagine have all of those kind of biological traits, readily induced nitrate reductase activity, that are quickly responding to the nitrate that's coming out in a submarine groundwater discharge plume. Yet we have no enzymology to actually test that idea. Imagine that these are all growing rapidly, that if we add nitrogen, their growth rates will double or triple, and yet we have few studies that actually look at them besides the ones that I showed you already. So those are gaps in information that I think are part of the important type of research that we need for the future.
And there's not enough fish because they've all been grazed out, fished out, or poached out?
In large parts of the number of fish that we have in the main Hawaiian Islands, it's been estimated to be about 25% of the fish that we had 100 years ago. Having said that, I have to say that with El Nino, things are changing. In the last summer, 2014, we had video cameras out looking at grazing experiments that one of my undergrads was doing. We didn't capture any grazing of the algae that we wanted, right? The cameras are focused on these plants that are in little feeders out on the reef. They didn't eat any of that, but what we saw in the background were clouds of baby reef fish that were coming through the reef. And those baby reef fish presumably came in with El Nino, They have maybe not so many now because it's been more than a year, but they've got to be bigger, the ones that remain. And that's coincident with the observation many people have now that Waikiki and on Maui and in Kaneohe Bay, the algae are gone. So increasing herbivory might actually have a big effect in drawing down the biomass of all natives as well as invasive algae. And that's why it's so important to include in these discussions about submarine groundwater discharge as a source of nutrient for the algae. But grazing could come in and change the dynamic for the benthic community dramatically. I think it has. Not to mention the hurricanes that we and the storm surge that we've had and the swells and the tsunami that are churning things up in our reefs. Those are also going to have a beneficial effect in exporting the biomass of these invasives that sit on the reef out there. Okay, so this is a very dynamic time actually. I'm in conversations with some people about using the mechanical force and the grazing pressure, using this window of opportunity that we have as a natural experiment to start outplanting native species back into the reefs, especially in Waikiki where we knew they occurred in the 1960s. So that's a whole other set of research experiments, but we have settled germlings of sargassum on tiles. We just need DAR to give us the okay to start planting them out onto the reef. But back to submarine groundwater discharge. This is what happens when you've been in the one position for too long, right? Lots of different pots are boiling over. Hypneomuciformis is an alga that came in. It was an intentional introduction to Oahu and then probably caught a ride on some of the inter-island navigation, some of the barges probably. It was introduced to Maui about 1988. It started to show up in blooms like this. So this is what a bloom looks like. It's a large biomass rolling around in the water. You can see this is not really clear, clean water, and a large amount of it stranding on the beaches. One of the very first calls that I got as an assistant professor long time ago was, what do we do with this stuff? Do we chop it up and throw it in the ocean? No! Get it off the beach, but please don't throw it back in. Every little piece that they could chop up from a big mat like that would just start to grow again. That's the simplicity that these plants have by being such well-adapted plants for an ocean setting. At this point, this is apparently the biomass that's difficult to find now while we're in this El Nino period, but at an earlier time, the county would run a bulldozer over these beaches to scrape the biomass up off those sands so that people could use the beach. This is in Maalaea in the late 1980s. So nobody was swimming in this water, nobody was sitting on the beach, lots of flies and kind of nasty stuff going on there. The other kind of confounding issue with Maui County is they have an ordinance that prevents sand from being removed from the beach. So if this stuff comes up on the beach, it's got sand all over it. And so the bulldozer could only pile it up in a big berm in the back. They were never able to take it off the beach because it had sand on it. So as that algae is rotting up at the top of the beach, where's the nutrient going? Right back into this big culture vessel that's sitting right here, right? This kind of embayed, slow moving, little bit of wind mixing, big body of water. So that's where where the first interest came. We have class 5 injection wells regulated by the EPA. You probably know a lot about this from the various speakers. The Department of Health was looking at trying to preserve the drinking water, and so they regulated all of the injection wells to be in this region where there was brackish water, so there would be the underlying aquifer was not considered a drinking water source here, and there wasn't considered a drinking water source because it was brackish. Right? Brackish water is not good for us, so what they were trying to do was to prevent any kind of injection well in these upper Malka lands. This is a little bit off up the hill, but still relatively low in terms of its position. So the injection wells were cited in the effort by EPA to protect the drinking water, but in the process, they set them in the worst possible place for their impact to the coastal environment. And when you look at these reef regions, and skip that, these just show the ejection. Yeah. When you look at through the Chip Hunt study from 2006, the ejection wells are actually continuous with the coral reef region in this area. This is from his modeling study that was done, not the Hunt and Rosa executive study that I asked, or summary that I asked you to read. This was really the first piece of fundamental information that allowed us to start changing the narrative in the discussion with Maui County. They were adamant that there was no way that the nutrients that were going into the ground could be tied to the algal blooms, even though the algal blooms were literally in the coastal margin, right below where the receiving waters were being contaminated or tainted with that effluent from the injection wells. In 3 different locations on 3 different parts of the island, here in Kihei, up in Lahaina, and then up in Cottonwood. So this ended up, the Hawaii Coral Reef Initiative actually hired an economist pair from Dutch gentlemen who came over and did economic assessments of the nuisance algal blooms in this Kihei, Maui area, and found that they estimated a cost of $20 million in lost revenue and property tax associated with the bloom. $20 million. The hard part for the county, assuming that they would acknowledge that there was a relationship between the well and the blooms, the hard part was for them that they never saw those 20. It was lost money. It was not money that they ever had in their pocket in the first place. And so they were being forced to try and figure out how to solve this issue without having additional revenue. How many people live on Maui? Anybody know? About 100,000 people. That's it. That's 1/10 of what we have on Oahu. The property tax base, which is what the county has, is very small in contrast to what we have on Oahu. They simply had no capacity to consider alternatives, and so I think, in my humble opinion, they chose to ignore the problem rather than to embrace the problem because they were so cash limited. They had 100,000 people as resident. How many tourists visit this island a year? 2 million. So they have 3 to 5 million gallons of waste per day being generated for those 3 locations. Okay. That's a lot of wastewater to deal with, when in fact what the economy was based on is 100,000. Craig, do you want to comment on that? No?
No, I was trying to remember, I read this paper, but was it mainly tourism? Was it 20 million?
Yep. No, 20 million in lost revenue, and that came from the value, so it's indirectly tourism. If you were to buy a condo in one complex in the Kihei area where the tides were rolling with bloom algae, and or over in Olivalu or another place where there's clean water, the differential in price was much lower for the condos that were in the bloom area. So there's lower property value. That's part of the tax. That's part of the loss. There's lower property value. There's lower tax base that's brought from that. And what was nice about this study is that they actually had a developer that built the same floor plan in several different locations, one with algae and one without it. So they were as fair and direct a comparison as possible. So this has several different parts to it. That was certainly one. It's an indirect way. If the tourists want to buy a condo, then they would be part of that problem, that of realizing that money lost. Okay, so it's quite clear now that we've got the effluent coming into the injection well and it moving down, being carried by the groundwater so that the plume is heading out into the coastal area. But that was mathematical. This was a model. This was not empirical data. So we had an initial $50,000 grant and then followed up with other monies to understand the biology of the organisms to generate some of the empirical data that would allow us to evaluate and refute the contention from the county that the wastewater never made it to the coast, that the algae would grow in it. There were all manner of things that were thrown up as statements that were made for which we had no data, so we set out to try and demonstrate that there are in fact is a detectable signal that comes from wastewater, and that the plants would in fact grow, grow substantially, flourish under these conditions. So if you collect Maui if you collect Hipia on Maui, you can see that it comes in a variety of different colors. So what are these colors? These are the photosynthetic pigments that the plants have. With a full high nitrogen environment, what we see are really deep dark plants. Their color is black, and that's because they are taking in, these are red algae, they're taking in all that nitrogen that's available, that we now know from work by James as well as Dan Amato, maybe in the range of 300 to 400 micromolar nitrate in the pore water coming out into coastal areas. So it's more than 10 times, 20 times the background nutrient level that a plant would see. This is the color that they are under general low nutrient. So there's none of that deep dark phycobilin that costs the plants lots of nitrogen. When the nutrients are high, the plants are deeply pigmented. I saw some ulva today at the New England Research Center that's got a well that's pulling nutrient-rich water for theatrons. They have ulva growing in their tank. So even this green alga, not a red alga, under a high nutrient regime was almost black. It was the first time I'd ever seen a different color group besides the red algae turn this deep dark color. Plants are going, if given sufficient nutrient, they're going to acquire it. This would mean that they should be able to photosynthesize and grow rapidly when we catch plants that are these colors. With some of our very early caging experiments, plants were put in that area where we estimated the plume to be, right in this region. The algae that were in cages doubled their weight in 2 days. Imagine if you had a bank account that had that kind of return on investment, right? We'd all be happy. The normal growth rate would be, maybe 3% per day. This is 50% per day. Right? This is an early indicator that the nutrient loading into this reef region was substantial. But nutrient is one thing. A signal that's tied to a source is another. And so here are the conditions where we have high nitrogen, medium nitrogen, low nitrogen, and then medium phosphorus and high phosphorus in an experimental matrix that made it put together. What we did was to directly address the issues for the ability of algae that are causing blooms to grow on wastewater. She set out a set of experiments that looked at growth, photosynthetic performance, tissue composition, the delta 15N, which I hope you all understand by now, and the nutrient uptake rates, which is measured by the disappearance of the nutrient from the water, not an enzymological assay. We had 7 different treatments that were set up. No nutrients added, 25 mils per liter up to 200 mils per liter of wastewater added to the containers in which the plants were grown. And we did a number of different experiments. This is the kind of manipulation. Here's a diving PAM being used in a lab setting. We now have a different junior PAM, which is a lot easier to work with. The plants were acclimated to low nutrient water for 7 days because by this time we had already learned that they had to be stripped of their background levels. And then the experiment started. So by eye, you can see what's happening. Here's day 0, and for all of them at the beginning, they are nutrient starved, they're not nice, they're very unhealthy yellow, looking kind of sick, they're not particularly robust plants. By day 3, these plants that receive no additional nutrients are still pale yellow, but we're starting to see a rapid change in the pigmentation. By the time look at the size change that's taking place. These are liter beakers. By day 6, at 200 mil out of 1,000, so a 20% wastewater input, the plants are clearly darker and bigger. And by day 9, they're deeply, darkly pigmented and have attained the highest growth rate. We have the actual growth rate data to show it. There's delta 15N values to show that they're actually also incorporating. And I think this is the visual signal for the clear responsiveness that the plants have So presumably, within this short period of time, going from here to here, these plants are inducing a nitrate reductase system, a nitrite reductase system, paying the economic, the metabolic costs for that nitrate that they can then assimilate, and pumping it into their metabolism, synthesizing the pigments for photosynthesis and rapid growth. Okay, here are this is the percent in wet weight over these different experimentals. You can see that the plants that attain the highest growth rate with the greatest amount of sewage effluent added. Okay, so it's quite clear the plants can respond to this wastewater. That's not an issue at this point anymore. And if you look at the delta 15N values for Hypnea and Ulva in these two experiments, we see that, that's actually already published information, that's not in review anymore, but you can see that the delta 15N as an experimental period, as the concentration increases, we see the increase in delta 15N of those tissues analyzed for the ratio of the 15N. So the delta 15N is revealing the ability of the plants to acquire wastewater. We now have a label that helps us identify the source for the waste, or the source of the nitrogen that the plants are using as they attain these growth rates. White Kulani as our no nutrient background level. Here we see the increase in sewage. Over time, we see an increase in the delta 15 and up to values of about almost 30. The other important point to note is that there's not a lot of difference. There's some, but there's not a lot of difference between the Ulva and Hypnea. So these two plants are responding fairly similarly in their response to the ambient nutrients, even though they're of different evolutionary lines. Ulva is the green blade, Hypnea is this little cylindrical form. So it's quite clear that the plants are responding similarly as a result of us having pre-treated them so that they couldn't rely on their internal pools that they have in the tissue.
What was the N15 of the fluid?
That's a good question. And we have, this is at a time, I don't have the data for that. This is at a time when C. parabicole was supplying us material. And at the period, he was the manager for the Lahaina wastewater treatment plant. He was told not to communicate with us anymore. We never got the actual sample set aside to run for the signal. So we don't know what the water values were.
Lahaina effluent's up around 30 though.
Okay, well that's great to know.
It's already heavily denitrified, so the concentration of nitrate in that water is probably around 200 or so, maybe 250.
Okay. Thank you, Joe. So, pretty darn close to what Joe's reporting for the water for this species. The dark diamonds are the Hypnea and the triangles are the Ulva. We then are about contemporary with this experiment. We actually just went around the island, Megan went around the island and sampled plants from those environments as noted at these different locations. Not necessarily all the same species. It's not common to find one species in all these places. And so this is kind of a famous map at this point showing that as you go into areas that have low level of urbanization, the delta 15N values in all the tissues analyzed are fairly low, representing a low level of input of wastewater. As you go into areas where there's a high level of urbanization and population density, we see strong indications of land-based sources of pollution getting into coastal areas. Okay. This was work funded by AppScore many years ago.
I was going to ask about that. I didn't know you wanted to say.
Huh?
That was a previous AppScore project.
Yes, very long time ago now. There are reasons, I think, for us to be cautious in taking this kind of approach, going island-wide and going across all the samples of algae that are available And I come back to the discussions of different metabolisms and different photosynthetic capacities and different adaptive strategies that the plants would have. It is, in a way, lucky that all of these species seem to have fallen in line with what our expected results were. But for this to be the most robust, you would want to have one species that you would be sampling across all these. Now, there were, I think, up to 6 taxa that were included in this analysis, and green, brown, red kinds of things. So this I think, is, however, a strong implication for the role of land-based sources of nutrient that are making their way into coastal environments, all from field-collected material, not manipulated in any way. Okay. We continued this kind of measurement. They kind of went over the top in looking at the analysis along a very uniformly spaced set of samplings around the coastline in the area in the vicinity. Here's the line of wastewater treatment plant. This is published data, where you can see the numerical value changing as we get close here to the Katakili Beach site, which has become a famous location now, as shown by Dr. Glenn's studies with the tracer studies that have been done up here in the effluent showing up in less than 90 days out in this location. So we saw values in the range of almost 40 parts per thousand. There's a value down here at 39.2. Meg went in with the manipulations using these cages, so this gives you a sense of how we actually handled the deployment of manipulated tissues. These are little cages that are anchored to the bottom. They have little floats. These are often placed close to the seeps or in experimental areas, so it allows us to space them in a uniform way if that's part of your experimental design. These are clearly not really disruptive. Here's some shrimp, some squid that are hovering in the area. It allows us to come back and sample them on a regular basis so that we can do a variety of different kinds of manipulations that give us what she was calling a kind of real-time delta 15N value. Here's the wastewater treatment plant again, and these represent a set of sites. You can see that we actually attain values that are now above 40 in these onshore, offshore kinds of gradients. So there's probably a field of release, not just a single bubble or a single boil like we see over in Wailupe. This is what those seeps look like. There's a kind of Schlieren mixing as the fresh water, warm fresh water reaches the salty, a little bit cooler coastal water. Bed values again at 42 down to 17 in that area right around the Katakili Beach Park, which gave us a two-dimensional model when you put this together. This shows a clear, strong plume in this vicinity, not too far from the wastewater treatment plant. And I think it was Chip Hunt who suggested that this actually may be following an older, an ancient riverbed, which might allow actually for the conduit of the wastewater.
Actually, what it was is there's a buried river channel that's a barrier to the north of it.
Oh.
For its flow, it's part of it.
Nice. So that would be up above the plant. And that actually makes a lot of sense. When these early studies were done in the 1980s by Peterson, they were looking up in the north area up here and just hit the tip of some of the signal for the Delta 15N. Nobody realized that there might be this movement to the south. And so it's great to have actually got the data that come from the tracer studies.
So that last picture, if you go back to that, when Henrietta gave her talk, after her seminar, I came in a little bit late, I saw her showing the video of the bubbles coming out of the seafloor. That was right there. And what you were looking at was nitrogen gas that was being produced, and that was being liberated from nitrogen production. As opposed to converting it to N2 gas.
Unbelievable.
We call it the champagne hydrates. I felt the champagne field because there's thousands of bubbles coming out all over the place.
It's really hard to get the bubbles into the little funnel.
Yeah, so when we analyzed it, my first guess working, I have a ancient history working in anoxic type of environments, and I thought there was going to be methane and hydrogen sulfide, which are more anoxic type of degradation processes. We talked a little bit about this before. but it had reached this nitrate reduction threshold.
Right, and so that would have allowed, because of the bacterial activity in the denitrification, that would have allowed for the reduction in the overall load from the wastewater plant to the value that was here as it's coming out into the coast. And I think, Joe, you had said a few years ago it was about 5 micromolar nitrate.
Yeah, at this specific time, like when we took those gas samples and we're doing this study, like well over 90% of the nitrogen in the wastewater was being reduced by the time of discharge. But since then, you know, they did their chlorination for a while, and that's allowed, or I think that that's allowed the nutrient levels to come back up to levels near the actual wastewater level.
And that actually is a really interesting set of observations, because I talked to my friends at the Division of Aquatic Resources. You probably all know, maybe you don't, but maybe you should know, that this Kaakiliki Beach area has actually been set aside by the state as an area that's managed for no take. And by that they mean there's no take of herbivores from this 1.5 kilometer stretch of coastline. So the state has closed it. And the goal was to have increased herbivory get up to that level that would actually regulate the invasive algae that used to be so persistent here. They didn't realize, I suspect they didn't realize, that the nutrients in the plume as it's coming out had been so altered through bacterial metabolism that it was very low by the time it came to this level. And in the background, the algal biomass under a low nutrient regime had started to decline, actually substantially. The biologists at DAR attributed that to the fish grazing.
Well, you don't know that it wasn't.
I don't know that it wasn't, but it would be difficult for a plant community to sustain a large biomass as it had with 5 or 6 micromolar nitrate. And
It
so
could have been both.
it could have been both, but in the process they weren't sampling the nutrients at the same time as doing the fish counts. And so what's been called the miracle of Kaakiliki, the herbivore management area, is actually probably a little bit more complicated, and it raises a real, in my mind, a real concern for the application of a herbivore management area in other locations. It's not going to be enough, I think, to control the herbivores unless you can also, increase the herbivore pressure, unless you can also simultaneously draw down the nutrient supplies that are coming into some of those areas where the blooms are the source of concern. So we have to be smart enough to carry these two sides of the ecosystem in our views of these as we design experiments. It's got to be nutrient supply, but it's also got to be the biological role of grazing pressure. Associated with this is also the public health concern. Here's some of the bubbles that you can see coming up out of the ecosystem, out of the sediment. And these are just tourists that are swimming in the area. If nutrient metabolism is drawing down the nitrogen load in that plume, then I would imagine that there's a substantial biological community also coming out, and that could be a number of nasty things. So thanks to Dr. Glenn and his patients working through that and his team, we now have a report that actually shows that we have an 84-day time frame for the nutrients in the well actually coming out surfacing. That's an important contribution. I want to highlight one other part of what Meg did with the algae used in cages in order to assess the different sources or different sources of nitrogen coming into the ecosystem. She used a system like this that was offshore. It actually had a series of floats on it. It was deploying these transects that went from shore off into deeper water. We had to get Coast Guard permits in order for this. They had to have lights on them so people wouldn't run into them at night. To this, she attached these nutrient-stripped ulva species into little cages in these locations, allowing us over time to collect a 3-dimensional map of where the plumes were coming actually into this nearshore environment. This is published information. You can see the color of the Delta 15N scale here on the bottom, the wastewater treatment plant up here. These are the sites for the transects with the algae. This is not an easy way to view it, but if you can imagine, this is the northern end, this is the southern end, and these green regions are along the coastline. These don't reflect where there's alga abundance. It reflects the delta 15 end value, so mid-range about 14, of the algae that have been tied off in this kind of system in the water. So there are clear conduits in this region here. That's a higher value, somewhere in the range of about, it's like 22. That's, I would think of it as kind of like a pipe of discharge in this region that's being detected by the alga. Here's another one at some spatial distance where there's a hot sample coming off, and then others, clear area, and then another site of discharge at a lower region. What's fascinating to me is that these discharges, Craig, I'd be really interested in your interpretation of this as well. As time goes on, there's fluctuation in the signal that the algae are reporting as this kind of tape recorder for the input. So this is February, which may have been a fairly wet month. Here's April. We see a hot spot up here, some background loading, but much lower levels in April, and then another hot spot way down here at the bottom. I was stunned to see the level at which the plants are responding from 1 month, 2 months later to the reported, using the same assay, the same floats, same locations, differences in the flux into the ecosystem. This is up in the water column. This is not down actually in the subterranean plumbing down here. So that's April. Here's May. We pick up another signal that was probably close to the one that's in the mid-range, but drop off everything pretty much down here. And then June. So there's clear hot spots up here and a kind of variable signal down here to the south. And is that related to the rainfall? Is that related to the amount that's coming into the wastewater treatment plant? I don't know. Craig, do you have any?
Joe?
I think that might be related to the physical oceanographic parameters. Like, you have to look at tides, currents, waves. Like, there could be the same amount of nutrients coming out at the same place, but if waves and currents are doing different things, they could be exporting those nutrients in different directions. They could be mixing the ocean at different
Sure,
levels.
that's fair, certainly.
needs to be
And yet
accounted
the delivery and its persistence in those coastal environments is really quite dramatic from a biological point of view. And I think, to me, that's unexpected. I don't know, maybe that's being naive in terms of physical processes in the coastal setting, but it's, if you were phytoplankton in this area, it might give a very different signal from time to time.
Were there any physical parameters recorded during that stretch? I mean, or is it just placed out there, so there's no rain data, no wind data?
There's no rain
no
data, there's no
wave?
wind data. Right.
Probably very dynamic in
Yeah.
terms of what's happening there with waves and currents
Right.
daily, weekly, and monthly scales.
The other thing that that did come from this as well was the realization that a lot of this buoyant plume actually came right to the surface. And so a lot of the biological phytoplankton mediated production that's going on in the coastal surface waters might be more directly affected by these kinds of plumes than what you would see at deeper locations. So for what these are worth, I think that they illustrate just how profoundly dynamic this ecosystem is and how good the plants are at collecting this information, providing some integrated data sets. So we have that information. I think the last point that I want to probably make is to highlight this graph, again from Scott Larned, that shows for one alga the kinetics that we have for the dissolved inorganic nitrogen growth rates. This is Dictyosferia cavernosa. This is the bubble algae from Kaneohe Bay. This has got a long history of responsiveness to nutrient pollution, maybe not so much submarine groundwater discharge, but it's the only alga that we have where we have growth rates as a function of nutrient concentration. And when we see that there's a saturating dissolved inorganic nitrogen level at only about 17 micromolar, we start to put the plumes from submarine groundwater discharge into some context. Larned's earlier work showed a 6 micromolar nitrate stimulus in terms of growth for a number of our algae, maybe many of our native species only require a relatively low level of nitrogen in order to saturate growth. This may be one of the ways in which we can start to distinguish the capacity of a native species from invasive species. There's a whole lot more work that can be done using these kinds of approaches, as well as the tying them to the submarine groundwater discharge issues that are the principal supplies for these kinds of nitrogen in the environment. So I invite you to have any questions, throw them up here, and we'll continue to talk, but I think that's a good place to do this.
Okay, thank you.
Study.